talked about the range of probabilities, how the range goes from 0 to 1. 1 is in certain. 0 is impossible to happen. You can keep your probabilities in fraction, decimal. How many places do we say for decimal? 3 decimal places, 3 decimal places, or a percent. Generally, if you're talking like subjective probability, you're pretty much talking percent. Weather, percent. You don't want to hear your weather forecaster say, well, it's predicted that 3 out of 5 days will be rain. So you want to hear, what's my chance today of rain? Remember the 3 types of probabilities: theoretical, empirical, and subjective. Subjective is the one that has a little bit of extra gut feeling in there. So watch for that one. The complement, again, the complement works real well. Is the everything but that. When we start doing probability things and we say the probability of someone getting a hit at bat is 1 out of 3, then therefore the probability that they don't get a hit at bat is its complement, 1 minus 1/3, 2/3. We use the complement case. Complement with an 8, not a 9. You can also do it like when you're using a frequency distribution. If you want to know, in example 7, we use this and we said, what is the probability of selecting a random social work network site worker who is not 23 to 35 years old? That means you would have to add up all these other ones. Instead, you can take the total and subtract the one that you have. So if I take the total instead, minus the 23 to 35, and put this over my total, that would work out the same. This is using the complement situation. It just helps you from adding everything else but that one, which kind of makes sense, right? Okay. A couple of the applications, and we looked at trees. I think trees are important, so I do trees right up front. A probability experiment consists of tossing a coin and spinning a spinner, shown at the left. So let's walk this one through. So you have a spinner. At the left, we're on page 139. You have a spinner that has how many sections to it? 8. All of those sections have to be the same size. If you have something that looks like this, and say this is white, and this is black, and this is green, you need to make probabilities. Everything has to be the same size. So you would have to cut this guy in half so that each one of these was a quarter. And the white is 1/2, but this would be 1/4, this would be 1/4. Not 1/3, 1/3, because they're not equal. So this one would be half. So make sure that before you look at something, you realize that they're all equal. So there's 8 sections to your spinner. How many possibilities when you flip a coin? 2. So therefore, what will our sample space look like? 2 times 8. We should have 16 outcomes in our sample space. The spinner is equally likely to land on each number, meaning it's a fair spinner. Everybody gets 1/8 of the time. So they want us to use a tree diagram to find the probability of an event, tossing a tail and spinning an odd number. So our tree diagram is going to start with tossing our coin. That's a good way to start it. So we're going to toss our coin. We're going to start with me, or you, and we're going to toss this coin. What could you get on this coin toss? Heads or tails? What's the probability of this? 50-50, so 1/2, 1/2. Now, from here, we're going to spin a spinner. What's our possibility on a spinner? 1 out of 8. So we're going to have 8 of these guys. 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4, 5, 6, 7, 8. And because they're equally likely, each one of these is 1/8. So if you multiply this across, 1/8 times 1/2 Each one of these occurs 1/16th of the time. 16. Ah, 16 we got because when we multiplied 2 times 8, we got 16. So we knew there were going to be 16 parts to this, right? And again, if you spun a tail, if you toss a tail, you have a chance to spin the spinner, and you have a chance to do 8 again. Here's where you find your 16. If you add up all of these last branches, there's 8 there and 8 there. There's your 16. Your sample space is just follow your tree. Heads 1, and do we see a pattern here? Isn't there a nice little pattern here? And then 1 for tails. Sometimes we don't even need to make a tree, but since they asked us to, we made one. Okay, all of these come on the probability of 16. Sorry, 16. 8 times 2. So the probability that I toss a tail and get an odd number. So I'm in my tails category. This is like a good reason why you separate it into the next row. How many of these are odd? 4. So 4 out of 16. And you could reduce this down to 1/4. Okay, getting a heads on the spinner, or I don't like the or yet, but we'll do the or spinning a number greater than 3. Does it say or in your thing here? What's 2/3? 4 out of 16. 16, sorry, 16. Does it say or in your book as well? I don't know why they threw an or in there. Okay, so here's the difference with the or. It would include all of them. I can get all the heads, I can include all the heads, or spinning a number greater than 3. Now, here's my numbers greater than 3. Just watch here for 1 second though. If you count all of your heads, you've already had these numbers in here. So you're not going to be able to count them twice. I can't believe they did this one with an or in it. Alright, we'll do it anyway. Now, these guys, we're never going to get these. These are the only ones we actually don't want. This is like a complement case. You want all of these, you want all of these. The only thing we don't want is 3 of these. So 13 out of 16. Or 8 of these, 5 of these, 13. We're going to see in the next unit on an or why we don't add them twice. Because they've already been counted for the heads part. So I already counted that, so I can only count it once. What if it said the probability of tossing a head and a number greater than 3? What would that be? What is it? Tossing a head and a number greater than 3. 5. 1, 2, 3, 4, 5. These are the only ones that I would be able to use. See the difference between the and and the or? This would be 5 out of 16. So our sample space kind of helps us work the probabilities. The or works a little bit different, which I'm surprised that was an or, but that's okay. All right. Your college identification numbers consist of 8 digits. Each digit can be 0 through 9. So how many possible digits do you have? 10. Always remember there are 10 digits. I need 8. What is the probability of getting your college identification number when randomly generating 8 digits? Each digit can be repeated. You have 8 pieces in your ID number. So how many choices do you have for your first one? 10. For your second one? 10. All of these are 10, right? And what do we do to these guys? We multiply them. So an easy way to do this is 10 to the 8th power. So 10 to the 8th power is a very, very large number. 100 million. There's 100 million different combinations there to making somebody's college identification number when things can be repeated. That means we can possibly get all zeros, which is really not a number. Yeah. Well, you know how you get zeros on your jersey? Yeah. Kind of the same thing. Right? Isn't it? People get zeros on their jerseys. All right. What if the first two digits, now your identification number consists of 9 digits. The last 2 digits of each number will be the last 2 digits of the year you're scheduled to graduate. The other digits can be 0 through 9, and each digit can be repeated. The first two digits of your number is the last 2 digits of the year. So say you're graduating in 2016, that has to say 16. So let's consider, if you graduated here in 16, this has to say 16. Did these have any restrictions? No. So in how many ways can we get a 1 out of 10? Only one way, right? In how many ways can we get a 6 out of 10? Only one way. So now when you multiply these, you get 3, 4, 5, 6, 7, 10 to the 7th power. Okay, what is the probability of getting your college number? Hang on. Now, these are how many ways you can do this. Here is the difference. What is the probability? You're only going to get one number, 1 out of this guy. That's the probability of getting your college number. There's a difference between ways and probability. Probability has to be between 0 and 1. We always calculate the ways first, and your number is unique to you. No one else is going to have your number. So 1 out of your possible totals, this can be. Make sense? Good? All right. Tomorrow I'll give you a little class assignment, since we kind of wasted today. We'll talk about the probabilities a little bit more tomorrow. All right. And by the hours are all off too.
Oh, really?
Yeah.
Oh, yes, it's 7.
Yeah, the hours are all off as well.